And the purpose of this video is to give you a little bit more support and a resource, a video resource on Kirchhoff's laws. So we'll use the problem from a practice quiz and we'll walk through it in a little bit more detail and kind of explain what's going on. So first thing I want to draw your attention to is just the current as indicated. So in general, you could pick what current directions you want to use. The problem has them indicated just to kind of simplify things for you a little bit. But I want to point out that the current everywhere in this part of, in this loop, this part of the loop would be the same. Same with this one. This would all be I2. And then I3 would be everywhere in the middle. So there's just the one resistor in the middle. But I just want to make the point that all of those elements that are in series have the same current. All right, so the first part of the question asks us to write down basically the equations that we can get. So let's do that. If we look at this point here, we can write a junction equation. The current going into that point, I1 plus I2, is going to have to equal I3, the current that's leaving. All right, so we have one expression so far. The other expressions that we can get from each of the loops, this loop, and then the loop all the way around the outside, which is related to the first two. So let's do that. Let's assume also that we're just going to go around clockwise, at least initially. So if we look at loop 1, let me give it to you like this. So we basically have loop 1, loop 2, and then loop 3 would be, all the way around the outside. So if we look at loop 1, the equation that we're going to have, and let's start from this lower left-hand corner, you'd have, and if we're going around clockwise, you'd have a factor of E1, increase in voltage as you go through that battery. Then you'd have a drop, i.e. negative I1 R1, voltage drop from that resistor R1. You'd have negative I3 R3 from the current going through that resistor, and then a negative I1 R4. So notice, be careful about which currents you're associating with which resistors. That's partly why I drew this line, to help you explicitly connect the fact that I1 is going through R4, while I3 is going through R3. You don't want to get those mixed up. Now, something I want to point out to you here, you could go the other way around the loop. So if you go around this way, if you go counterclockwise, and let's start at the same corner, notice what's going to happen. So this would become positive I1 R4 because you're going upstream. It would be the potential here would be higher than the potential where we start, so it'd be a positive factor of I1 R4. Positive I3 R3, positive I1 R1, and then negative E1 as you go from the positive to the negative terminal in the battery. Now notice this equation and this equation are the same. This is just multiplied by -1. You multiply this second version of this by -1, you get the same thing that we got initially. So it's the same expression. It doesn't matter which direction you go around the loop when you're writing your loop equations. All right, let's look at the loop 2 and loop 3. So loop 2, let's do the same thing. Let's start in this corner and just go around clockwise. So you'd have a factor of positive I3 R3. So you go through R3. You'd have a factor of positive I2 R2. Positive I2 R2. And then we would have a factor of negative E2, the voltage from that second battery, second source. And then we're back to where we started. This would equal 0. And then from L3, third loop, you go all the way around the outside. What are we going to have? We would have E1 minus I1 R1 plus I2 R2 minus E2 minus I1 R4 equals 0. Now, notice you can get this last equation by adding the loop 1 and loop 2 equations together. So this isn't really an independent equation, but it can be useful, as we'll see in a little bit. So now we have 4 equations, really. One from the junction rule, and and 3 equations from the loop rule. So the next thing that we want to do is find our unknowns. So, and the unknowns that we have are all the currents. So we're going to assume basically that you don't know that I1 is 1 milliamp for the purposes of working this out, because I want to show you the logic. And then we'll also confirm that that it's working out as we expect. So we take our equations, and basically the problem now is 3 unknowns. I1, I2, I3. We don't know what they are. So the strategy is, we could set different equations equal to each other. There's really many ways that you could do this: substitution, elimination of variables in one way or another. And I think it's logical to just think about, to show you one example of going about this. We want to come up with a way to eliminate everything except one of the unknowns. So let's try and eliminate everything but I1. So put stuff in terms of I1. So let's do that. Let's try to solve for I1. And we're going to make use of the fact that the resistors, we're told that the resistors are all the same and that the voltage is 5 volts. So let's simplify our expressions a little bit based on that information. So from our equation I've labeled 2 here, what would we have? We would have E1 minus I1R minus I3R. Remember, we're just assuming that we're making use of the fact that all the resistors are the same. So this would give us an expression, and we also know that so let me just write it here. R1 equals R2 equals R3 equals R4 equals R, and then also the fact that E1 equals E2 equals E. So we're basically just putting that information in. So this would give us an expression that E minus 2I1R minus I3R equals 0. And then from, let's see, our equation that we have labeled 3 here, just simplifying this, we'd have I3R plus I2R minus E equals 0. And then also from equation 4, we would have E minus I1R plus I2R minus E minus I1R equals 0. So this one, there isn't anything to be further simplified, but notice in this equation from equation 4, this can be simplified further, and we get basically that I2R minus 2 I1R equals 0. All right, so to our goal, let's try and solve for I1. We can look in these expressions and see what we can easily eliminate. So notice from this one, this only contains I1 and I3. And so we can get from this the fact that I3, in terms of I1, would be, let's see, E minus 2I1R over R. So this would be, E over R minus 2I1 equals I3. So we have a simple expression for I3 that only contains I1 and the other stuff that we know. And what else do we have? So we'll make use of this. And then from this last one, we can express I2 in terms of I1. I2 is 2I1. Notice R and R would drop out. So we can make use of this as well. So let's put those ingredients into our, so our game plan then is let's put into I1 plus I2 equals I3, so our junction expression. Gotta give ourselves a little more room. So let's do that. So I1 plus I2 equals I3. So what is I1, or sorry, what is I2 in terms of I1? We would put in this. This is 2I1. And then this is going to equal E over R minus 2I1. So that's our expression for I3. Now notice we have something that only contains I1s. And if we put all the I1s on the left side here, we'd have I1 plus 2I1 plus 2 more I1. E over R. So in other words, we have 5. Write it here. 5I1 is E over R. So I1 equals 1/5 E over R. So we're told that E was 5 volts and R was 1 kiloohm. So 5 volts over 1 kiloohm would give you 5 milliamps, but we're dividing by 5, so that means that I1 is 1 milliamp. So then, how do we get I2 and I3? Well, we can just plug into our expressions from above. So I2 is 2I1. So I2 is going to be 2 times 1 milliamp is going to give us 2 milliamps. Okay. And then for I3, it's E over R minus 2I1. So this is going to give us 5 volts over 1 K, so 5 milliamps, minus 2 times I1. I1 we found to be 1 milliamp. So this gives us 5 minus 2, which is going to give us 3 milliamps for I3. Okay, and we can check our work. Let's see. So we know that I1 plus I2 is supposed to equal I3. So 1 plus 2 equals 3. That works. That's agreeing with our with what we expect. So we've found, in other words, we've used all the currents, or we found all the currents and just made sure that all the currents agree with what we expect. We don't find any contradictions.